Okay. Ready to go?
Yes.
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 So let's derive these controllers. So I'm going to start from this expression, which is basically having removed the omega E transpose in front of everything from the equation that equates the Lyapunov time derivative that I have imposed and the one that comes out of directly deriving the derivative from the V. Okay, so trying to find a piece of paper where that happened, but yeah, you probably have better notes than I do, and you can go back and track it down. Let me see. Yes, so we did get to a point where this was true. Okay, well then I'm gonna go one step beyond and and write the expression for JT dot. So because we did that, if you go back to our dynamics calculations, we had an expression for it that was quite convenient, and so that was 1/2 summation of these differences ysj minus ytj gamma j dot. Of course, I don't have space here, but this multiplies tj sj transpose plus sj tj transpose times omega error plus e. Okay, so this is just another way to explicitly write JT dot. But keep in mind that omega error dot is omega dot minus omega desired dot, of course. If you take now the omega dot from the full equation of motion with variable speed, contra-moment gyros and everything, you can prove to yourself that the following will pop up. So you will have summation of let's see, 1/2. Here we have ysj minus ytj that multiplies tjsj transpose plus sjtj transpose, and let's see, here we have omega plus omega desired. So what I'm doing, yeah, it's basically plugging in omega equals omega. It's the omega error in here. You can show that that's true. I'm going to find the actual full equations here in a second. One minute. And of course I can't find the full equations right away. I don't know where they ended up. Not in the trash, because I have them here. But yes, so the idea is you get the variable speed contra moment gyros equations, the full expression. Here it is. Here is the one. And if you substitute omega being omega error plus omega desired, you can get something like what I'm showing you. Okay, so there's that. So where was I? Omega plus ISJ of the wheel, TJ omega j plus YGJ omega x applied to GJ, and this whole thing is actually multiplying gamma j dot. So again, I'm skipping the steps, I'm just giving you the final. It's the same equation now, that the difference is that I'm using the definition of omega error. Let me finish writing it. Summation of YGJ, then GJ omega double dot J. So this is equal to K omega E plus E minus J total omega D dot minus omega X, I'm right down here, minus omega X multiplies J total omega plus, promise I'm almost done, WSJ omega J plus any external torques. So how do I get here? Well, again, through these two expressions, this one and the fact that this is the omega error. So if you plug in the omega error in here, this is what you get, and then you go back into the equations of motion and substitute it. Use the definition of omega error by saying that, well, obviously from here, omega dot is equal to omega error dot plus omega desired dot, and the same is valid without the dot. So by keeping in mind this expression for the omega error and these, you go into the equations of the full equations for the momentum exchange devices, where everything can change, and they will look like this. This is another exercise for you to do, but I think we've done enough of algebraic calculations, and you can definitely handle this. It's just substitutions. Now, this is the part where we start getting a little more serious about control. So we can collect things and write what you have in a more compacted manner by collecting basically the gamma j's, the omega j's and dots, and the gamma double dots. So in a compact manner, I can try to write B, the matrix B gamma double dot, plus C gamma dot, plus D big omega dot, equals everything else, K omega E plus E minus JT omega D dot plus this cross product, omega X, J total omega plus summation ISJW SJ omega J plus any external torques. What are those? Well, B probably should use it this way. Well, B is the following. First one is a metric with all the gimbal axes projected in the body of the spacecraft and up until the end, assuming that you have n momentum exchange devices. And then you have a diagonal matrix that only has the gimbal axis moments of inertia on the diagonal, and that's your B. Your C is going to be something similar to this, except it's the T vectors up until the nth one. Then you have a diagonal matrix with the wheels moments of inertia about the spin axis, and also the diagonal matrix of the angular velocities of the wheels. It's not done. Plus you have this omega x that multiplies the matrix of the g's all the way to gn. Again, gimbal moments of inertia only on the diagonal, plus, yeah, C is the ugly one, plus you have 1/2. Let's see what we have here. You have a huge matrix whose elements are T1 S1 transpose plus S1 T1 transpose that multiplies omega plus omega desired, and then you have n of these. So the last one is Tn Sn transpose plus Sn Tn transpose omega plus omega desired. And we're not done. This multiplies this difference. Symmetric matrix with the gimbal, with the spin axis moments of inertia. Minus this. Okay, that's C. D, much nicer. The S axis all the way to the N1, and then you have spin axis moments of inertia matrix. That's it. So once you have assembled these B, C, and D, we can write things even in a more compact manner the following way: B gamma double dot plus C gamma dot plus D omega dot. This has a dimension of a torque. You can show it to yourself, and we're going to call these T, or moment of the momentum exchange device. So, and everything that goes in here is, of course, all these bunch of terms: K omega E, total moment of inertia, desired angular velocity, time derivative, and this cross product, and the external torque. So everything goes in there. So this is the compact manner to write the equations of motion. Having used, again, the fact that I've introduced the angular velocity error, and I have introduced the equality between the Lyapunov time derivative that I impose and the one that comes from the candidate Lyapunov function. So I am using the Lyapunov function in doing this. I'm computing the dynamics on that function, basically. Okay, so there are different control strategies that we can use now. I'm going to start with this, and then we'll have to finish, I guess, this afternoon. The first one is velocity-based control. And well, let's say that, well, that's really what we're going to do in general, okay? Velocity-based control. If we have a CMG, which means that omega dot is equal to 0. By the way, no one has asked me what these gamma, generic gamma and omega are. Obviously, I guess it was obvious, but you know, I dropped all the superscripts, etc. Gamma is the vector of, oops, don't die on me. Okay, this pen is done. We'll continue with red. Gamma is the vector of all the gammas, all the way to n. Omega is the vector of all the omegas. the spin rates, all the way to the n one. Okay, just to be clear. All right, so my compacted equation, of course, becomes this. And you know, you're using only really this term, as we said. This is really not something we want to use as controller, so you can bring it here. In many cases, it's even ignored. But what's happening here is that if you have the rank of C that goes down, you may lose the ability to exert the desired torque. So it will create unreasonably high gamma double dot if you try to compensate with this. So no one ever uses this. So the singularity is also can be also seen as the determinant of C going to 0. While in a variable speed control moment gyro, where you have all these terms, as we said, if something happens to this one, you always have this other one. Actually, the way that we measure singularity is actually, let me correct this. Usually the parameter that is used is the determinant of C transpose. Anyways, that's how we check how close we are to being singular and not being able to do things with the CMUs. Okay, last few minutes, and then we'll continue. I'm going to introduce the control vector just to make things even more compact. I'm going to call that eta, and that's everything. I have the accelerations of the wheels, all of them, and then I have the gimbal velocities, all of them, just in one vector. And so now my compacted expression will look like Q eta equals momentum exchange device torque. Remember that this has all those terms that we've seen before, while Q is nothing more than putting D and C next to each other. And so I'm neglecting the B gamma double dot term. Or you can just move it here and make it part of momentum, the MED component, okay? Either way works. But definitely is not part of the controller. As you can see, the gamma double dot is not part of the control variables. All right, so what is still, I haven't told you how I'm gonna drive these things. Well, one is the one that I'm proposing that we implement. Again, it's not the only one. Is a constrained minimum solution for the controls. So we define a matrix of gains, W. It's a diagonal matrix that has gains for the wheels up to the nth one, and then gains for the gimbals, 0 off diagonal. We choose this, while for the spin we propose to use the following: some constant and then the exponential of minus mu delta. And so this is a constant, this is a constant, and this is the, again, determinant of C transpose. So by doing this, I change the way I give importance to the reaction wheel behavior, depending on how close I am to a singularity. So this is really for variable speed contra moment gyros. And you may recall the gentleman yesterday was working in Simulink that he had this mu, and we were confusing it with the gravitational mu. It is just one of the constants that you see in your initialized file for this matrix. And you will also have these other ones defined in there. And you can change them, of course, but I gave you some values. So I'm going to stop here because it's time. We'll continue in the afternoon. We're almost done finding the final control. And so, yeah, any questions? Then we start working on your real assignment. No questions?
Yes, in the if you can go back to the definition of the C matrix. I know it's difficult to find in the page.
Give me a second. It is.
The last term in parentheses in which we have omega plus omega desired. This term represents the omega error.
The what? I'm sorry, the omega?
Omega plus omega desired.
No. Omega minus omega desired is the error. So it is a little bit counterintuitive to see omega plus omega desired, but you can show that that's actually what pops up. If you take why did I make a mess with my papers? I'm so disorganized. If you take this expression here,
okay,
which is basically coming from the Lyapunov function on the right and the Lyapunov imposition of its time derivative on the left. So this is really the Lyapunov contribution to the discourse that we're having, and this definition of omega error, and you substitute this into the variable speed contra moment gyros equations, you actually come up with something like this, and you will see some terms that actually look like omega plus omega d. I know it's strange, but
yeah, okay. So it just needs some passages of the
it's a plus. It's a plus. It's not. It shouldn't be a minus. It's actually a plus. Yes.
Okay. Thank
you. If we have time, I can go through the calculations together, but that's pretty boring. It's substituting things.
Okay.
Yep. So from basically from let's see, from this equation here, you have omega error dot, you have which is equivalent to omega dot minus omega d dot. So substitute these into omega error here and here everywhere, and extract J total omega dot, omega of the spacecraft, and plug it into the equations for the variable speed contra moment gyros, and things will start showing up the omega plus omega desired.
Okay.
Yeah. Other questions? Okay, I'll see you in a couple of hours. No. Yes, 2 hours.
Yes.
See you later.